All right, let's say you have a state space system like this. You have two states, x and y, and that is your state vector. So your state vector x is x and y, and it's got derivatives like this. This is your A matrix, this is your B matrix. You have one control input, u. And I want to apply PD control. Let's look at PD control in a control block diagram, and let's take a look at what we want. So if I want x command, I have a command vector that I'm going to run through here. And I'm going to run this through my PD controller, and that's going to create u. And then that's going to hit my, I'm going to say my transfer function or my state. And that my state vector is going to pop out x. I'm going to do full state feedback, so I'm going to measure all the states. I'm going to get an error signal here, and that's going to be a vector. And then u is going to be equal to PD times this. Okay? So, in order to apply this kind of control, you have to think about u and e and PD, right? In a transfer function world, PD would be some sort of transfer function with s's in it, but in this case, you have a scalar, right? U is a 1 by 1, and e is a 2 by 1, and you want this to be linear. We're doing linear controls. And so if we're doing linear controls, it means I need some u multiplied by something times e, which is going to be x command minus x, y command minus y, and I need some matrix here that's going to take a 2 by 1, right? That's my error vector. This is e. And I need to multiply by something to give me a 1 by 1. Well, if you look at the inner products, this needs to be a 1 by 2, which means I need something like this and like this. And so I'm going to put a k1 and a k2 here. This k1 here is your proportional gain, and this is your derivative gain. Now, it's kind of, this is kind of a weird problem to pick because normally you would have x dot and x dot here, and you would have x dot and x double dot here, but it's really irrelevant. This derivation that I'm going to do is going to apply for any state space system under the sun, okay? So the idea is that that is your state space system there, and I'm going to call this u equals k e. And this is going to be u is k x command minus x, okay? K is this matrix here, this is my error vector, e is x command minus x command minus x. What I'm going to do is I'm going to substitute it in here, and this is where I'm telling you I'm going to create this derivation so it applies to anything. I'll do it for this example, but this derivation here is going to apply for everything. Let me get to a different marker here. Okay, so what I'm going to do is I'm going to take my system in state space, x dot equals ax plus bu, and I'm going to substitute in this equation. So I'm going to get x dot equals ax plus b, now k, x command minus x. And if I carry out the multiplication and simplify, I'm going to get x dot equals a minus bk x plus bk x command. And so what you look at here, this is your homogeneous solution, homogeneous, and this here is your forcing function. Okay? So B is typically, we're not even talking about that. B is designed by the state space system. K is really what you have to determine. So what do you make K? Well, it really comes down to this here, right? In order for this system to be stable, remember, how do you determine stability of this system? You need to look at the eigenvalues of A and the real component of the eigenvalues of A need to be less than 0, right? Well, now you have a closed loop system where you have A minus BK. So what you need is the real component of the eigenvalues of A minus BK to be less than 0. That is what you require. And so that equation applies to any state space system out there, even 5 or 6 by 6 systems. The difficulty, of course, is computing this by hand. So let's see if we can do this problem by hand and shake out what we get. Okay, so I'm going to take a picture of this board. Okay, send that off. And now what I'm going to do is I'm going to rewrite this equation up here. the eigenvalues of A minus BK. This is what we need to compute. And so we're going to compute that here. Okay, so here we go. So first, let's compute A minus BK. So my A matrix is 3, 4, 2, negative 1. My B matrix is negative 4, 1. My K matrix is K1, K2. This is a 2 by 1 times a 1 by 2. So when you multiply this out, you're going to get 3, 4, 2, negative 1, minus, you're actually going to get 2 by 2. You're going to get negative 4K1, and you're going to get negative 4K2. And then you're going to get 1K1, 1K2. If you don't know how to multiply matrices, I feel bad for you. It's not easy to learn. Hopefully your linear algebra teacher did their homework and taught you well. So I'm going to carry out the addition now. So 3 minus minus 4 is 3 plus 4K1. 4 minus minus 4 is 4 plus 4K1. 2 minus K1 is just 2 minus K1. Negative 1 minus K2, there's a K2 here, sorry. Negative 1 minus K2 is negative 1 minus K2, okay? And this is A minus BK, okay? So how do you get the eigenvalues of this matrix? Do you take the inverse? No. You just take the determinant. So all you need to do is take the determinant of SI minus A closed loop. I'm going to call A minus BK my closed loop state matrix. So now I just take S, I'm going to put bars here for determinant, 0S, that's S times identity, minus 3 plus 4K1, 4 plus 4K2, 2 minus K1, negative 1 minus K2, and then subtract those now, and so I'm going to get S minus 3 minus 4K1, negative 4 minus 4K2, let's see, I'm going to get a negative 2, so I'm going to get a K1 minus 2, and then I'm going to get a minus, so I'm going to get a 1 plus K2. And then I just take the determinant of that. So now I'm going to get S minus 3 minus 4K1 times 1 plus K2 minus, I'm going to pull the minus sign out, so I'm going to get plus 4 plus 4 K2 times K1 minus 2. Okay? I feel like I'm missing an S. There should be an S here. S plus 1 plus K2. So that would change this to S plus 1 plus K2. This is going to equal 0. And then you need to solve for S. But you also need to solve for K1 and K2. So what do? Well, what do you want the system to do? Well, I want the system to be stable, right? So I need the real part of the eigenvalues to be in the left half plane. So you can pick whatever you want, right? You can do pole placement and just put them wherever you want. So let's just make them negative 2. And I'm just going to critically damp the system. Keep in mind, what you really want to do is do this. You, the control system designer, needs to pick zeta and omega n to be what you want. And then you need to factor all this out. So you're going to get S squared plus S1 plus K2 minus 3 minus 4K1 plus negative 3 minus 4K1, 1 plus K2 plus 4 plus 4K2 K1 minus 2 equals what? Well, guess what? This term here is 2 zeta omega n. this term here is omega n squared. So you have two equations, two unknowns. You could try and solve that by hand if you wanted to. I personally would just plug it into a computer. All you need to do is solve for, if you pick omega n equals 4, and that means omega n squared is 16, so you would do 16 equals this. And then if you set zeta equal to 0.5, it means 2 zeta omega n is 2 times, that's 1 times, it'd be 4. And so you set 4 equal to this, and you distribute and solve. And that is how you solve for K1 and K2. So if you were given any state space system, you could use this formula, eigenvalues of A minus BK, to tune your dynamics such that your closed loop dynamics have whatever natural frequency and damping you want. Okay? If you have any questions, post in the comments. I hope you enjoyed this lecture.